Good morning, grade 10s, and welcome to another physical sciences lesson. So yesterday we started with chemistry and we went over the ideas of solution. And then I think it was Braden who was late, and I seen Braden's not here either today. Oh, he's going to be angry at me. So yesterday I promised you I'd put everything in the drive, and then of course I slightly forgot to did. But that's okay too, because I'm human and I feel like I'm having to be superhuman at the moment, but that's okay. Right, so today, as promised, we are going to revise the periodic table. Okay, good morning, Ben. You seem new. I haven't seen your name before unless you've just always been hiding in the shadows. So today we're going to revise the periodic table, okay, specifically focusing on electronegativity, the thing we kind of whacked our heads against yesterday, okay? And then I'm also going to very gently start touching on the idea of how we can go from mass to moles and back again. Okay, right. So today is mostly a revision day. Tina, I'm very glad you love the periodic table. I love it too. It is like the ultimate crib note. Okay, so yesterday I did the writing on the PowerPoint thing. Everybody had a nice little laugh at me. That was fantastic. My tech would not work yesterday. But today we're back to good old whiteboard. Okay, so please remember, if there is a lag, okay, or if my audio goes or anything like that, just drop me a message, okay? But it looks like the audio is behaving, touch wood, and everything else is behaving. Okay, all right, guys, so just a reminder, all right? Know we've done this. Know many of you have done this ad nauseum so many times that you can do it in your sleep, right? That is absolutely fine too. I see Carolina is hiding in the participants list. Braden definitely overslept again today. Latavo's here. Larissa's here. And like I say, I see a couple of new faces that are always very quiet. Guys are more than welcome to speak up. Remember, this is your classroom too. Okay, so let's get going. Fantastic. So, this periodic table is exactly the periodic table you will get in your test and in your exam. That's why I chose to use this one. Okay. You'll see here at the top, it says Physical Sciences Grade 10. Pardon me, I pulled this one straight from your exam guidelines. The exam guidelines were set in 2015. They do revise them from time to time, but these exam guidelines are still what is considered the correct exam guidelines for grade 10. Hello, Tyrese, welcome. Okay, so a quick recap of this periodic table, okay? And guys, this key that you get here at the top, you get 2. So there's absolutely no reason for you to go, which number is which one again? I don't know. Okay, they give you this key. Like I say, this is the periodic table you are going to get. All right. So group 1 and 2 are metals, except for hydrogen. But hydrogen and helium are like weird. Okay, they're in level 1. They only have one electron orbital. You'll learn about that next year. And so, like, there's not much that these guys can do. Okay, they're quite limited. And hydrogen, oh, okay, I will get it back up. Hydrogen is not a metal. All right, please do not think that just because hydrogen is in group 1 it is a metal. It is not. It is a non-metal. Miss P, I've also been very guilty. I haven't loaded up your special stuff for you. I will do so straight after the class as a promise, but I will give you the drive anyway. All right, so metals, then we have our transition metals, all right? And if you if you remember correctly from the last time we did this, okay, I said to you guys that there is a staircase that splits the metals and the non-metals. All right. So the first thing we are going to do is we are going to draw in the staircase. And now I'm going to be sneaky, and I'm going to use the straight line thingy-mabobbin. Okay. Guys, I haven't forgotten about you asking for the drive. I've just got it loading in the background. Okay. There it is. Shareable link. Dunk. And go. Right, so there is the drive link for you. Okay, it doesn't change. That is the one that you guys will always use. All right, so let's add in our staircase. The staircase is what splits the metals from the non-metals. Okay. Pleasure, Misty. Misty's new too, unless my brain's completely losing it. Right, so, come on, pen. Right, so our staircase. Oh, I want a line, not a block. Line. Good, here we go. We're growing in numbers, family. So our staircase splits our metals and our non-metals. Even with a straight line, I'm not really good at this, clearly. Eek. There we go. Right, so that red line there splits my metals from my non-metals. You guys will still remember this. We did it not too long ago. Oh, I say not too long ago. I think we like talking here early April. All right. Okay. So that splits my metals from my non-metals. Okay. Then, if you guys remember correctly, I said that we have a few metalloids. You guys remember that? Metalloids. Right. Shall we go green for metalloids? All right. Metalloids are either side of the staircase. Semi-metals. Yes, Poppy. Good. Okay. So for metalloids, I don't want to color in the whole block because then you guys are like not going to see. But here we go. So for metalloids, we have boron. We have silicon. We have germanium. Arsenic. And then the ones we never ever use. SB. DE. And BO, palladium. All right. So those. All right, Arthur. Sorry, I forgot about 80. 80 is one of those weird ones. Like, is it a halogen? Is it not a halogen? Is it a semi-metal? Is it not a semi-metal? Yeah, no one really knows. Okay. So these guys are either side of the staircase. Okay, the only one that's a bit of an anomaly is aluminium. And I hope everybody's pretty happy that aluminium is a metal. Guys, honestly, the ones here at the bottom, like 80, I know is antimony just because it's weird. But some of these here at the bottom, like BI, I don't memorize what the symbol means. Okay, because I know I can Google it. The ones I use a lot, I have memorized. Okay, cool. So those are semi-metals. Then we have our non-metals and we have our metals. Okay, now you'll remember way back in the day, I said to you guys, we have diatomic gases. There are 7 of them. H2, N2, O2, F2, Cl2, Br2, and I2. Okay. And when I say that they are diatomic gases, it means that in nature, you always find 2 atoms together, and it is always in a gas. All right. The only other gases on this periodic table are the noble gases. So I've just given you a shortcut way of being able to tell me whether something is a gas or a solid. Okay, so our gases are H2, N2, O2, F2, Cl2, Br2, and I2, as well as our noble gases. Everything else on this periodic table at room temperature is a solid, except, anyone know what the exception is? It's a metal. It's got 2 names, one scientific and one like more adventure-y. Mercury. Good job, Shane. Okay, so Mercury is the one on this periodic table, Hg here at the bottom, okay, that we find in liquid phase. What do they call group 8? Group 8 is known as the noble gases. Noble gases. They are called the noble gases because they are so lazy that it is very, very hard to make them react. Okay, they're like nobility. They just sit on their throne and do nothing all day. Right. All right, guys. And then when we started looking at how we combine elements, no? We said that the metals are like the men in a relationship and the non-metals are like the women in a relationship. Okay. And this, I think, is where you guys all realize that I'm not quite your average teacher. All right. So the metals give electrons. They donate their moolah. Yes, come on. The noble gases are like, they're not less reactive. They're like super duper unreactive. Okay. So the metals donate their electrons. They give moolah. The non-metals take electrons. They want moolah. Okay. On the periodic table, electrons are the currency. Okay. Right, guys. And then we also spoke, do you guys remember? Group 1, when it bonds, makes +1 because it gives 1 electron. Most reactive element. I think francium here at the bottom, right? This big oak here at the bottom is beyond reactive. Like you have to be so careful when working with francium. You can't even expose it to air. It just like spontaneously combusts. Okay. If you have time, go Google francium in water and check that reaction out. That is insane. Okay. Right. So we remember group 1 +1 when it bonds because it donates 1 electron. Group 2 +2 when it bonds because it donates 2 electrons. Do not try and understand the transition metals. They are weird and wonderful, just like you. Then if we get here, halogens, Tino, are group 7. I'm getting there. Just hang tight. Then group 13 has got 3 electrons. Okay. Most of them are metals, so they like to donate. Group 4 or 14, here we start with non-metals. Okay. So they'll either take electrons or here at the bottom, if they are metals, they will donate electrons. Okay, like we said, carbon, weird and wonderful. Okay, weird, weird, weird and wonderful. Then we get to group 15. They have some other weird name, which I can never remember. They like to gain electrons. Okay, so group 13 becomes +3. Miss P, I'll get there now. Group 13 becomes +3. Group 14 becomes ±4. Group 15 becomes -3. Group 16 becomes -2. And now we get to Tino's question. Group 17 or 7, these are the halogens. Okay. They gain 1 electron and then the noble gases do nothing. The Roman numeral here at the top tells us, then you are 100% correct, how many valence electrons each of these groups have. Okay, Ben is 100% correct. Ben, I'm trying to find a color. Oh, we're just going to go black. Okay, so the Roman numeral tells us how many valence electrons, and it tells us what charge. Okay. When I was in school, incidentally, we didn't have the other numbers. We only had the Roman numeral numbers. I don't know why they changed that. That happened sometime in like 2010 about. Okay. I think the transition metals were feeling a bit left out. And so they also needed numbers. Okay. So the Roman numeral tells you how many valence electrons. So it can tell you what charge. Cool. All right. And we know that noble gases are lazy. They are boring. And so we know that all atoms want 8 electrons, 8 valence electrons. And this is what we call the octet rule, the rule of 8. Okay, easy peasy, guys. Easy, easy peasy. Right. Now, what I want to focus on today is the thing that blew your brains a little bit yesterday, is these electronegativity stuff. Okay, so you ready to understand why water is a dipole better than we understood it yesterday? Okay, right. Do you see that almost every number or almost every element has an electronegativity? All right. There are those who do not. Noble gases you see has none. Okay. They do not attract other electrons. They're lazy. They're boring. Okay. They don't react. And you'll see, especially down here at the bottom, you'll see that a lot of these guys also don't have electronegativity numbers. Okay. So Ben asked, does it mean that noble gases' outermost shell is full, giving them no charge? Yes. So Ben, noble gases, their outermost shell for valence electrons is full, which means that there is no space for them to react with other atoms because there is no space for more electrons. Okay. Under the right circumstances, you can make them react, especially lower down. Helium and neon, very unlikely that you're going to get them to react. Argon in very, very specific situations, like very. But krypton and xenon, you can make them react. But the reason why, if I start explaining it to you, I'm going to blow your brains even further. Okay. So for me, it's always easy to remember that the noble gases, their outer shell is full. There's no space for more electrons. Okay. And sharing and transfer of electrons is ultimately what makes things react. All right. And that is why the noble gases don't react. Okay. let's get back to electronegativity. All right. The definition of electronegativity, I did give this to you before, okay? The definition of electronegativity is how strongly does an atom pull other electrons towards it. Okay, I'm going to say that again. Electronegativity tells me how strongly does that atom pull other electrons close to it. So bonding electrons or transferred electrons. Okay. And there's lots of things that influence electronegativity. You do not have to know that for exam purposes. Okay. Electronegativity tells us whether electron transfer is going to happen or electron sharing is going to happen. And it tells us if electron sharing happens, which of the two atoms is going to pull those shared electrons closer to it. So I'm going to use yesterday's example. We tried water, and I tried to get you guys to dipole. Yes, Ben, exactly. So yesterday we tried to do water, and we tried to get to dipole. Okay, so that is what we're going to focus on today. Before I get there, please remember that ionic compounds is metal and non-metal. Then we have metallic compounds, which is metal and metal, duh. And then we have covalent, which is non-metal plus non-metal. Okay, I am going to write that down again. Right. So let's add a page and let's start thinking. Here we go. So, most important thing, ionic bonds or ionic compounds is metal plus non-metal. Okay? Covalent equals non-metal plus non-metal. And for today's purposes, that's all we have to think about. Okay, we don't have to worry about metallics. We did both covalent and ionic yesterday. Okay, the ionic one we looked at yesterday was sodium chloride, table salt. So we looked at sodium chloride yesterday. And the covalent example we looked at yesterday was water. Clearly, example doesn't want an L. All right. We can say this is ionic because it's a metal, sodium, and a non-metal, chlorine. And we can say water is covalent because H, hydrogen, non-metal, O, oxygen, non-metal. Now I want to show you how we can think about it in terms of electronegativity. And because we all know I can't spell, and we all know that I take shortcuts, I shorten electronegativity to EN. And most textbooks do too. So I think I'm okay. Right. So I'm going to pop back to the periodic table, and we're going to look at the electron negativity of sodium and chlorine. Right. That one. So the electron negativity of sodium is 0.9. And the electronegativity of chlorine is 3, right? So let's choose a different color. Sodium has an electronegativity of 0.9 and chlorine has an electronegativity of 3. All right. Now, guys, I just want to say to you that that means that sodium does not pull its valence electrons towards it strongly. A small electronegativity means, meh, you know, if someone wants my electrons, that's okay too. I'm like not seriously attached to them. That's okay. But atoms or elements that have high electronegativity, they go, oh, no, 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 mine, 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 or mine. Okay, they're like the seagulls in Finding Nemo. Mine, 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 mine. All right. So now people are going, oh, but man, you know, like 3 is not that big. Just remember, for some other random reason, the smallest number for electronegativity is 0.9. And the biggest number for electronegativity is 4. Okay, so that's your scale. So a scale anywhere past 2 is stronger, and anything below 2 is like, okay, right. So can you see on this scale, chlorine has a relatively high electronegativity. Okay. Now, the electronegativity of each element doesn't actually help us. The thing we are interested in is the difference in the electronegativity between the two. Okay, delta, difference in electronegativity. So I always go big number minus small number. We are not interested in the sign. We are simply interested in how different are they. And now I get 2.1. Okay. And with 2.1, I can do a lot. Okay. 2.1 tells me that one of these two atoms is going to seriously attract the bonding electrons towards it. And what do we know about ionic compounds? Do they share electrons or do they transfer electrons? Take a stab. Ionic, do they share or do they transfer electrons? Arthur says share. No, you don't need to do a calculation, Misty. I just want to know, in general, ionic compounds, do they share or transfer? Tyler, welcome. Silas says transfer. Okay. So, Arthur, you need to remember, oh, Tyrese is also reading with Arthur. Okay, so, ionic compounds transfer electrons. Okay, so if you see the word ionic, then there has been a transfer of electrons. Okay, you guys remember yesterday when we had sodium, we said sodium loses its valence electron, becomes positive, and it gives it to chlorine, that then becomes negative. So there was an electron over here that has now been transferred to chlorine. Okay. And covalent shares electrons. Okay. So if we look at water, that these electrons between hydrogen and oxygen belong to both oxygen and hydrogen. Okay, so this here shows a sharing of electrons, where ionic transfers electrons. And that makes sense with this electronegativity difference. Okay, this electronegativity difference says, well, chlorine really wants these electrons. Sodium's kind of going, meh, I don't know, maybe not. And so chlorine will take the electrons of sodium. Okay. We're going to see in a moment there's actually a range. Let's have a quick look at the electronegativity of hydrogen and oxygen. Hydrogen 2,1, oxygen 3,5. 2,1, 3,5. Okay? So we said 2,1 and 3,5. Now be careful that this 2 doesn't throw you, please. We only look at each bond. Okay? So I calculate the electron negativity of each bond, not of the molecule. There's no such thing. Okay? When I calculate electronegativity, I calculate the electronegativity of a bond between two elements. Okay? So for electronegativity of water, I'm going to go 3,5 minus 2,1, which is 1,4. Can you see here? Ionic, close to 4. Covalent, closer to 0,9. Okay. So that is how we use electron negativity. Now I'm going to just look at water, because this is the place where yesterday we all went to say, whoa, what? Okay. So as you guys all know me, my board skills are horrific, so I've run out of board. Luckily, electronic boards, you just click next page. Go. You guys all know Lewis structures, hey? It's not hard, it's not complicated. There is the Lewis structure of water with oxygen's 2 little lone pairs. Miss P says she doesn't know Lewis structures. Miss P, I will make a little video / slideshow for you and pop it in the drive, and it will say Lewis structures. Okay. And anyone else who needs some help with Lewis structures can also have a look at it. Okay. So on the previous page, we calculated that the electron negativity difference is 1,4. Okay. And this one here, its electron negativity difference is also 1,4. It's a bond between an oxygen and a hydrogen. Okay. This means that these 2 electrons, the ones that bond oxygen and hydrogen, get pulled closer towards the oxygen and away from the hydrogen. Are electrons positive or negative? Come on, electrons, positive or negative? Negative. Come on, I want opinions. Negative, negative, negative. Okay. So we're all pretty comfortable with the fact that electrons are negative. Hello, Kieran. Brayden's still sleeping. Okay. So, let me just zoom in. Oh, go away. Go away. Right. So if these bonding electrons get pulled closer towards the oxygen, can we all see? No, we can't because the page just moved, but that's fine too. Can we all see here that this part of the molecule becomes sort of negative and this part of the molecule becomes sort of positive because hydrogen has lost its electrons? Okay. Now, yesterday we all looked at that sign and went, hey, say what? Basically, you draw an 8, but you don't finish it. And this is called a dipole. That's what that sign means. And it means sort of. Okay? It means that the electrons here get pulled closer towards oxygen. It doesn't get transferred. Now you need to be careful. The electrons do not get transferred. They get pulled closer. They are unevenly distributed. Very, very important. And so oxygen becomes sort of negative and hydrogen becomes sort of positive. And the same thing happens here. This side of this bond becomes sort of negative and this side of the bond becomes sort of positive. And now I have a positive part in my molecule and I have a negative part of my molecule. So I have 2 poles of opposite charge. And yesterday we said that is the definition of a dipole. The definition of a dipole molecule. Misty, yes, we are basically talking about polar molecules. Okay. Water is defined as covalent because it shares electrons and it's non-metal and non-metal. But because it has 2 poles, we refer to water as a covalent polar molecule. Okay. And that's, I think, where we got stuck yesterday, is this idea that these electrons are get pulled closer to oxygen. So oxygen becomes sort of negative. Hydrogen loses those electrons because it's got a smaller electronegativity. And so it becomes sort of positive. And because we have 2 opposite charges, we call this a dipole. And effectively, we say it's covalent because it's non-metal and non-metal. Polar because it's got 2 charges. All right. So that's where the idea comes in of polar and non-polar molecules. So there's a range for these guys. It is not compulsory for grade 10, but you are going to deal with it in grade 11. And in grade 11, they almost think that you know it already, which is why I want to teach it to you. Okay? So, if something is ionic, then I can guarantee you the electronegativity difference. Larissa, I've seen your question. I will answer it in a moment. Is bigger than 2. Okay, some people say 2,1. I generally go for 2,0. But you need to keep in mind that it has to be a metal plus a non-metal. Okay? Then when we talk about covalent, we can either have a polar molecule, or we can have a non-polar molecule. Ooh. Okay. So again, covalent means it's non-metal plus non-metal. Okay. For polar, I need an electron negativity difference of bigger. Again, there's dispute about this. The official one is 0.9, but if it's easier for you to remember 2 and 1, for now, that makes more sense for me. Okay? But obviously, it has to be smaller than the ionic one. And non-polar just has to be smaller than 0.9. Again, you can just remember the value 1. Here you could remember 2. All right. So Larissa asked, what's the difference between a compound and molecule? Now, Larissa, that is also a very, very contentious point. Like very. The easy answer is that a compound is the chemical product of 2 or more elements. So any chemical bond that is formed between 2 or more elements is referred to as a compound. It's compounded. And molecule, the word molecule, is specifically reserved for covalent compounds. That is the best answer I have within the South African curriculum. Okay. There are different people that feel differently about it, but within the South African curriculum, that is how we deal with it. So compound is any chemical more than 2 elements. Molecule is specifically a covalent compound. Right, guys? No, not there. There we go. Right, so that is what we have time for today. I had like really big on here, my next little thingy. Whoops, I don't want to send it privately. My bad. Hang on. For a last time, there's the drive. I have a private lesson at 11, and then I'm hunkering down and doing your drive. Okay. Tomorrow, we are going to start with different types of reactions. Okay. It's okay if it's hard. It's okay if it's new. Okay. We can do this. We've done it now for 8 weeks. We can do this. Right, guys, I will see you guys again tomorrow. Same place, same time, same link. Booyah. Don't forget about the I know, Miss P. I know. I'm blonde. I need reminders. Guys, thank you so much for joining. I hope you have a fantastic day. Enjoy your coffee. Be safe and be warm. Bye.